All right, so we're finding the roots of a polynomial, and we're going to start with this thing called the fundamental theorem of algebra. We have two things in math that have this kind of title. We have the fundamental theorem of algebra, and we have the fundamental theorem of calculus. So we're going to start with the fundamental theorem of algebra, and then in a couple of years you guys might get to the fundamental theorem of calculus. All right, it sounds big and scary. This is what it says. Every polynomial with complex coordinates and a degree greater than 0 has at least one root. All right. So why this is confusing in the book and what's going on here is the complex coordinates, right? So we're not talking about something that looks like 2ix plus 6, all right? It's not complex in that it has an imaginary component, but the real numbers are a part of the complex numbers. So what it does look like, what we are going to have is something like this: 2x plus 6 equals 0. What's the degree of that polynomial? 1. How many roots does that have? 1. What's the root? Close. -3. So all the fundamental theorem of algebra says is if I have a degree of 4, I'm going to have 4 roots. I have at least one, I'm going to have 4. They're not all going to be real numbers, they're not all going to be nice numbers, but there's going to be 4 things that I plug into that thing and I get 0. So that's all that's saying. I mean, it's pretty fundamental. It's just a starting point of we're going to have some solutions to 0. All right. So if we start with the general polynomial, we have this notation. F of x, so there's my function notation, is a sub n times x to the n plus ... plus a sub 2 x squared plus a sub 1 x1 plus a sub 0 or a naught. All right, we're going to use this on Friday to talk about the rational roots test. So we want to look at the notation. The a sub n is a coefficient. It's a number. It's a real number. It goes in front of the x. What would the degree of this polynomial be? What's my highest power? N. So it's an nth degree polynomial. This ... is an ellipsis. It means the pattern just keeps going. And then the a sub 0, what type of number is that? Is that a variable? That's our constant. That's like the plus 6 up here. Okay? So we have our constants at the end. And this is called our leading coefficient. It's our highest coefficient that goes with our power. So if we have, in this case, our leading coefficient would be 2. But we're looking at what goes in front. And then our power, our degree, it's called the degree of the polynomial. So if somebody says, build a 6th degree polynomial with the following roots, you know that your highest power is going to be 6. Okay. And again, all this is saying is that if I have an nth degree polynomial, I'm going to have n roots that I'm looking for. So they could all be imaginary, just like we're looking at this parabola that doesn't cross the x-axis. I might not have real numbers, but I'm going to have something that I can plug in that I'm going to get out of 0. And it's going to match the degree of the polynomial. All right. Thumbs up if you're still with me. Okay, good. All right. So what are roots? Can anybody tell me what a root is? What are we talking about? Jessica.
Oh, sorry. Something that makes the whatever part of it equal to 0.
Good. And then, great. And then Camilla, what were you going to say?
Where it crosses the x-axis.
Where it crosses the x-axis. Good. Anything else that we could talk about it? All right. There's really, I think it's 4 different ways that this could look. So if I say c is a 0, that's the same thing as saying c minus x is a factor. That's the same thing as saying f of c is 0. That's the same thing as saying c sub 0 is a x-intercept. So all of those, all four of those, are kind of our general thing for meaning roots. We're looking for things that I plug in and I get out 0. So if I say c is a 0, it means that if I put this in here, right, if I do x minus c, if I put in c for x, what's c minus c? 0. All right, so I'm going to be able to pull out that factor. If I plug in c into my function notation, I get out 0. And then this is what Camilla was talking about. If I have an x-intercept, that's where it crosses the x-axis. Y is 0. It's the same thing. All right, so those are all roots. There's my tree. Graphically is really kind of what we're going to build the bridge between. So we're going to do some algebraic work, but we want to build in the graphical part too. So if you looked at this graph, how many roots do you know at least exist? 4, right? I have 4 x-intercepts. Those are the roots. Now, does that have to be a 4th degree polynomial? It's going to turn out that it's not. I could have some imaginary roots that I'm not seeing, but I know that it's at least a degree of 4. All right? So I have 4 real roots. I might have some complex ones. We'll have to figure out how that goes down the road. But this is really the big idea of what we're doing. I'm looking for these things called roots. If I talk about a 0, a factor, an x-intercept, this piece here, the factor, is what we're really moving towards because we're going to use synthetic division to kind of pull these things out and get something called a depressed polynomial. All right. So at least 4. Blah, blah, blah. So we have this thing called the factor theorem. The factor theorem, we have the remainder theorem. So if f of k equals 0, then x minus k is a factor. All right, so it might sound like gibberish, but it makes sense. So what it's saying is if I plug this in, then I should be able to factor out that x minus k and get a 0. Let's try to look at y. And again, a root, 0, x-intercept, all of those things are going to mean the same thing. So if I take my polynomial and I divide it by this piece, I get some quotient and then some remainder divided by the same thing. So there's my quotient, and then there's my remainder. And so if this whole thing equals 0, right, I'm going to look at an example to kind of make it make sense here. So if I took this and I was to do my long division, what's going to go at the top right here? X. All right, I can do it with synthetic division if I wanted to too. I bring down the 1, and then I do what? 2 times 1, put it there, add, and go from there. I get 14. So I get x to the x, this piece, x squared plus 3x plus 4 over x minus 2 equals what? What am I left with? X plus 5, remainder 14. And the remainder we write as the number over the divisor. Now, this piece in here, this is called my depressed polynomial. And not depressed like we usually mean. That's not sad. Right? Why do you think it's called depressed? Kind of. What's the power? What's the difference? Well, from something squared, and now I'm writing it as something to the first. So I've depressed the power. I've brought it down a power. So I'm no longer leaning with the quadratic. Now I have a power of 1. All right. Well, this piece, what we have up here, the general function notation, and this is the same thing. My function is this piece, x squared plus 3x plus 4, and then my quotient is x plus 5. I have my remainder of 14. F of x, q of x, r of x. So if we multiply by x minus k, what am I left with on this side? If I multiply by this thing, what am I left with? Just the function, right? if I take this x squared plus 3x plus 4 and multiply everything by x minus 2, I'm left with just the numerator. Yeah? Okay. And then if I do the same thing on the other side, what happens here? I get that times my quotient, and I get my remainder times this, but the remainder is going to cancel as well. Right? If I plug in k, that's a 0. This whole thing goes to 0. I'm left with my remainder. So f of k is r of k. Because this should have brackets. All right. If you're still with me, you're doing great. Let's take a step back. All right. What we're saying is, if I plug in k and I get out 0, then it's a factor. Okay? If I do the division, this is a factor of the whole thing. Because what does this piece have to equal if I say that this is 0? What's the remainder have to be? 0. Which means that this goes away and I've factored my polynomial. That's all it's saying. And it makes sense. If I have the number 10 and I divide it by 2, what's my remainder? My quotient is 5, my remainder is 0. So is 2 a factor of 10? Yes. If I have the number 15 and I divide it by 6, what's my quotient? 2, remainder 3. So is 6 a factor of 15? No. If I take 21 and divide it by 7, what's my quotient? What's my remainder? Is 7 a factor of 21? Yes.
Wait, so what happened to like the cube of
This?
Yeah.
It's still there.
I know, but like in the bottom in the green with the 0 equals I don't
This piece here? Okay. So if I plug in k for x, k minus k is 0. 0 times the quotient is nothing. It's gone. So all I'm doing, I know this looks weird, is if I was to take the number 21 over 7 equals what? 3 plus 0 over 7, right? And then I multiply everything by 7, what am I left with? 21 equals 7 times 3 plus 0. The 7 down here is the factor. It's a factor. So it goes in, it factors out. When we look at it as a polynomial, it's the same idea. And I get something that is a depressed polynomial. Yes?
So if 7 is a factor, does that mean 7 is the root?
Not just for a number. Like a number is a number. It's never going to, it's not, I can't plug anything in and get out 0. But yes, for a function, it means if it's a factor, then when I plug it in, it's going to make the whole thing equal to 0. Yes, Nate?
What if it isn't? What if it isn't 0?
Then it's not a factor,
Okay.
which means that it's not a root.
Okay.
Okay? Because you divide it through and you get some remainder left over. This doesn't equal 0, so your remainder is something, so it doesn't work. It's not a 0.
Okay.
All right. Yeah, kind of. Let's keep going. So I have no remainder, so it's a factor. So what we're going to look at is if I took a big polynomial and I did synthetic division on 3, the number 3. I divided that through and I got no remainder. Is that going to be a root? Yes. If I divided it by x minus 4, so I put 4 and I did my synthetic division, and I got a remainder of 6, is that a root?
No.
No. That's all we're doing. It just looks scary because I have function notation and we have x's and powers and stuff like that. All right. Got it. Now, this piece here. Let's say that it's not equal to 0. F of k is 7. What's my remainder going to be? 7. Because I'm still going to put in this and it'll drop out. And I'm going to have the remainder is what the function is. That's called the remainder theorem.
Wait, but you already said that f of k is equal to r of
f of k, yes. So both of these, the factor theorem and the remainder theorem, kind of go together. All right? So if I have this, let's just do an example. Let's step away from the theory part and let's do an example, right? Is x minus 4 a factor? How are we going to figure that out? Divide by x minus 4, right? And if we get a remainder of 0, is it a factor?
Yes.
Yes. If we don't, is it a factor?
No.
No. So let's do it. All right. So I'm going to use synthetic division because it's quicker. And it's always, this is why I said synthetic is better for us, because if I'm looking for these factors, that's very convenient and nice that I have a way to divide that quickly, right? I'm never going to really want to divide by 3x squared plus 6. I want to know, how do these go in? So I bring down the 1, and then what do? I multiply to get 4, and then I add to get, let's see if I did this right. I multiply to get 28. I add to get 27. I multiply, and I get 110. I multiply, and I get 434. So is x minus 4 a factor?
No.
It is not. Okay? That's my remainder. And it's not equal to 0. So if I was to write it all out, all right, this piece, x to the 4th, 3x to the cubed, minus x squared, plus 2x minus 6, all over that is my division. What's this piece called? X to the 3rd plus 7x squared plus 27x plus 110. It's a suppressed polynomial because the power's gone down. It's also called the quotient, right? This is my remainder. Yeah? If I multiply everything by x minus 4, I get this. And I should have another bracket. So we can see I pulled it out, but it's not a factor because I still have this remainder here. But if I plug in 4, f of 4, what's this piece going to go to? 0. And 0 times anything is 0. So I'm going to left with f of 4 is 434. So f of 4 is 434, blah, blah, blah. That is the remainder theorem. So there's two ways that you can do this. If I just wanted to know if it's a 0, if I just plug in 4 into the function and I get a remainder, is it going to be a 0? I mean, if I get a non-zero number, it's not a factor. The reason why we want to go through this is if it was a factor, then I would have something that's cubed. I can deal with that. I can maybe factor it. If I can find another factor, what power would I have as my depressed polynomial coming out? 2. And we can solve every quadratic with the quadratic formula by factoring. So our goal is to start with a high power, break it down into a lower power. Can we get another root? If yes, then we're going to break it down to another power. If we can get it down to something squared, then we can get everything because we have the quadratic formula. All right. Yeah? Okay, we're about halfway there. I told you. Deep ends deep. All right. We have this thing so the stuff that I just went over is really, in my opinion, the important idea. Now we have some kind of tricks and gimmicks to help us. All right, so here's this guy, Descartes, his rule of signs. So we have this what's it called? Algorithm, I guess. If I want to know the positive real roots, it's the number of sign changes of the coefficients, f of x, number of sign changes of coefficients is the number of real positive roots, or it's less than that by an even number. So that's a mouthful. I'll let you write this down. negative real roots is the number of sign changes in the coefficients of f of negative x, or lessen it by an even number.
I know if it's a or less than, but even.
All right. So let's say I have an f of x. We're going to do an example. We're going to do the goal problem. So we'll look through it. Let's say I have 4 sign changes for f of x for this. So I either have 4 positive real roots, or I have 2, or I have none. If there's 5 changes in the sign for f of x, then I either have 5 positive real roots, I have 3, I have 1. If I have the negative one, let's say that there are 6 sign changes for the negative, then I could have 6, 4, 2, or 0. I can't have 5. And for this, you're just going to have to trust me and trust this guy, Descartes, that it works. All right, it's just a trick. We don't want to get into the how and why, or we'll be even more confused. All right, so why this is helpful is what we're going to do is we're going to, on Friday, get a list of all the possibility rational numbers that work. And we're going to go through and try to test which ones work, but we want to have some idea of why we don't have to test 10 different things if we only have to test 5. All right, so here's our example. This should be today's goal problem. So I have f of x is x to the 6th minus 5x to the 5th plus 3x to the 4th minus 5x to the 3rd minus 6x squared plus x minus 4. And I think I rewrote this whole thing. Stretching? Yeah. All right. So I have to write the function, and then I have to put in negative x into this. So if I put a negative number into x to the 6th power, is that going to change the sign of that value? No. An even exponent stays positive, right? If I put negative x into x to the 5th, what happens to this negative 5? It becomes plus 5. All right. If I put negative x into this, do I change the sign of the 3? No. If I put negative x into x to the 3rd, it does. It becomes positive 5x. This one doesn't change. And then x becomes minus x. And then minus 4. All right? All right. So now we count the sign changes. Do I have a change in sign from this to that? Yes, from positive to negative. Then it goes from negative to positive. Then it goes from positive to negative. And now it goes negative to negative. So is that a sign change? No. And now it goes negative to positive. That is a sign change. And now it goes positive to negative. That's a sign change. So I have 1, 2, 3, 4, 5 sign changes. So the number of positive real roots is going to be at most what? 5. Or it could be 1. It can't have 4 of them. I do the same thing down at the bottom. I don't have a sign change. I don't have a sign change. I don't have a sign change. And then I have a sign change. I don't, and then I don't. So how many negative real roots could I have? 1. I have 1 sign change. That's it. So I'm going to have some combination of that. Now, how many total roots am I going to have? 6. What's my power? 6. Right? So we're going to look and see how this works. And we're going to make a table. So I rewrote the whole thing a little bit smaller. I'm going to make a table. Number of positive real roots. Number of negative real roots. And then the last thing is going to be the number of complex roots. So those are the imaginary components. And I have to start with the total number of roots. When does this end? Okay, good. All right. So what's the total number of roots going to be? 6. Huh. That's going to be tough. 6. Let's see how badly I screw this up. Yep. Okay. And then what are my possible positive real roots? What's the most I can have? 5. Right? Or I could have 3. Or I could have, you're right, 1. Wow. Sorry, this was late last night. Okay. What's my combination of negative real roots? 1. All the way down. Okay. So, if I know that they're going to have to be 6, for the first line, how many complex roots am I going to have? 0. That's fantastic. That's what we hope happens. Because if I was to graph that, how many spots would it cross the x-axis at? 6. I'd have 6 real things that cross the x-axis. So that would be nice. If I have this, I already have 4. How many complex roots do I need? I need 2. All right? And then the last one, if I have 2, how many do I need? 4. Okay.
Wait, so should we not have 4 rows?
Huh?
You're not, you have 4 6s. But you were
Yeah, I shouldn't. I think I changed the problem and didn't fix it. So you should just have 3. So those are my combinations. Now, if I find, let's say we're on Monday, we're finding roots, and I've found 4 positive real roots. What do I know exists? How many should I have? I should have 5. Let's say that I'm solving this problem. I'm actually figuring out the roots. And I've already found 4 positive real numbers. Let's just say 1, 2, 3, 4 that I plug in and give me a 0. I know that there has to be a 5th one. And then if I know that, I know there has to be a negative one that I'm looking for. All right? If I find 1 complex root, I know that there's going to have to be another one. If I find 3, then I know there has to be a 4th. All right. The last thing that we have is something called the complex conjugates theorem, which says if a plus bi is a root, then a minus bi is a root. This is called the complex conjugates theorem. Okay. And this one's pretty easy to figure out why it has to be this way. So let's build an example. So I want to build a polynomial with roots of 3 and 4i. So what does that mean? What does it mean to have a root of 3? When I plug in 3, what do I get out? 0. It also means that it's a factor. X minus 3 is going to be a factor. Hey.
Hi,
Yep. Perfect.
thank you.
All right. So if I have that, what do I know about 4i? It's also a factor. Okay. Now, I'm not going to do it because we're going to have to undo it. If I was to FOIL that, is my imaginary component going to go away? No. The only way that i's go away is when I multiply it by itself, right? I squared is negative 1. So what I have to end up doing is I add the conjugate as another root. Because when I expand that, x minus 4i, subtracting a negative becomes what? A positive. And I still have x minus 3. So when I FOIL this piece, what do I get? X squared plus 4ix minus 4ix minus 16, what? I squared. So these pieces cancel, and I get x squared, and what does I squared give me? Negative 1 times negative 16 plus 16. We can see I don't have any imaginary components. All of that is then times x minus 3. I can figure out what that is by FOILing again, and I've built a polynomial that has those roots.
How were you like able to add, you call it the conjugate for like the 4i?
How was I able to?
Yeah.
Okay. Let's say that I just did it like this. X minus 3 times x minus 4i, right? Well, I would then get x squared minus 4ix minus 3x plus 12i.
Yeah.
So this imaginary component, this piece and this piece, blows me out of the water in terms of my polynomial. I can't have it. And then I'm not using the fundamental theorem of algebra. I can't do what I want to do. I need real coefficients.
Okay.
So I need the values, the constant, and the real coefficients to be real numbers. Otherwise, when I talk about even like graphing things, remember on the complex plane, we had the real numbers and the imaginary axis?
Yeah.
Well, I'm not graphing on that. I'm graphing on the xy coordinate plane. So if I have numbers that aren't on that coordinate plane,
So pretty much if it was like x plus 2i, then you just do x minus 2i.
yes. And if you had, let's say you had this, 3 plus 2i is a root. So one of your factors is x minus 3 plus 2i. Your other one is going to be x minus 3 minus 2i.
Please excuse the interruption. Hello, Miramani. It's Kendall. And Lily.